So today I would like to present my individual assignment. There's the title name, the velocity of fluid in the Bernoulli equations and the volume flow rate of the fluid for the specific condition. Okay. So for the introduction, actually we are using a programming C to doing all the programming. So programming C is so-called the high level and the general programming language of the purpose. So since the project requirement, we are using the loop in solving this programming C function. Loop actually is the sequence of instruction that command the system so that it can repeat the certain procedure under the specified condition and which the specified condition is achieved. And then later it will change, it will lift the load. So in this experiment, I'm involved using the Bernoulli equation. Bernoulli equation actually is the principle of conservation of energy. It includes the pressure, it includes the kinetic energy, and then the gravitational potential energy. So besides Bernoulli equations, volume flow rate also include in the calculation. So volume flow rate is the product of cross-sectional area of a pipe and the velocity of the water flow or fluid flow in the pipe. So next, we need to see about the problem statement. So as we know that the Bernoulli equation involves a lot of variables. So if we one by one insert it, it will be a wasted of time, as well as some calculation may make the error, as well as the volume flow rate. So we write this program, we can help to determine the velocity fluid of the velocity fluid and the volume flow rate for the equation under the certain situation. So besides that, we also can using the maximum range, maximum condition to determine the maximum velocity as well as the maximum volume flow rate under the certain parameter. And then since we know that there's a lot of variables inside, so we also need to know the problem we faces is what's the relationship between the variable, examples height, the density, and the pressure effects on the overall velocity fluid as well as the volume flow rate that involved in the system pipe. And then last, in the volume flow rate equation, they also involve the cross-sectional area of the pipe. So with this, we also need to determine what happened to the cross-sectional area, if they change, if they increase or decrease, what happened? Actually, how this affect to the overall volume flow rate. So for our objective is need to determine the velocity, fluid flow, and volume flow rate in the pipe with the given parameter, with the given limitation. And then the second objective is to determine the maximum value of the volume flow rate and the velocity with the certain parameter under the specific limitation, is to determine the maximum level. And then last, it will be determine the effect in the difference of height, various density, and change in pressure. That means effect of changing the variables, for example, height, for example, the density, it will affect the flow and the trend of the results. So we need to determine how it's affected. Then the last, also the area. The area will also change as volume flow rate at the result. So these are the four objectives we need to achieve during this report. So methodology. So we are using the formula of Bernoulli equations. Since we know that Bernoulli equations are involve a lot of energy conservation, so each of them we are need to calculate it. And then value of velocity is directly input to the next equation, which is QD equals to AB. So as we know that the responding variable for the Bernoulli equation will be the velocity. So using this velocity, we can input this value to the volume flow rate so that we can find the volume flow rate. And then loop technique to constrain the limitation of each parameter. That means in this report, we are using the range on a certain limit so that the loop can function, as well as there will be no over limit or no extreme cases in this procedure. So every parameters after passing through the reject, they will make a small increment or decrement so that it can continue to run the whole program. The condition is all within the limitation. Okay, now is the flow chart. So before that, I'm using the user input method. That means I'm required to the user to key in what value they needed. That means they are customized values. So they need to require 4 values. That means DH is the change in height of the pipe, and then the P is the density of the fluid. Then the third is DP is the change in the initial and final pressure of the of the pressure of the water and the certain situation, and then the last will be the cross-sectional area. So first of all, the gravity is 9.81, and then the volume flow rate will be Q, and then here got two max. So max 1 will be the function, the output for first function, that means is the velocity, and then the second one will be the output for the second function, that means is Q, as well as max 2. So when the user is input the certain value, for example the DH, they will input as H, and then H will must smaller than 2. If not, there will be non-function. They will go to the end and then end the function. So if yes, so it will continue to roll. That means it's the small p is the density of the volume. So with this, if the density of the volume is below than 1000, that means within the limitation, so it will be function well, continue. If not, go back to the initial condition, and then with the increment of 0.1 in the change of height. Okay, after that, they will continue the process upwards. And then P, if the density is smaller than 1000, that means it fulfill the requirement. So we continue go down with change in pressure, press. So the change in pressure, we have a limitation within 2000, within 500 until 2000. So if it's fulfill the requirement, that it will continue go down. But if it's not fulfill the limitation, it will continue go back, and then with the decrement of the density. The density will from the initial value and decrease one by one until, and then repeat the loop. After that, if the change in pressure are fulfill the limitation, so with these three equation, if these three variables are fulfill the limitation, so it can form velocity. Okay, and then with this form velocity, and then they will form a V, the change in velocity. Okay, the change in velocity can, if it is more bigger than max 1, okay, so they will go back with the loop and then increase P, increasing the changing of pressure, then repeating the loop. Okay, until the maximum value of 1, that means is V is equals to the output V. So after that, you just finish the first function, then we go through the second. So second function will be the Q equals to AV. That means it's the volume flow rate equals to velocity times the cross-sectional area. So as we know that max 1 is the velocity. So max 1 times A equals to Q, max 2. Okay. So A equals to A. So we have the limitation for area is maximum 50 millimeter. So A, we have the maximum limitation of 50. So it cannot avoid more than 50. If not, they will end the procedure. So from this, if yes, they continue proceed the equation Q equals to AV, and then if Q is smaller, is bigger than maximum 2, so the A will be go back to loop and then by increment 1. So if not, Q equals to max 2, it will continue the procedure. You will display max 1 and max 2 as well as end the procedure. So with this, we can find out the maximum, the value of velocity and the value of volume flow rate. So based on the flow, based on the diagram, so we can come up with a result. So since as told before, the range of the parameter is different in height, we have the 0.1 until 2. And then the density of the fluid, we have used 500 until 1000. The range of the pressure will be 500 until 2000. The range of the cross-sectional area will be 10 until 50. So as using a simple example, so we are using the DH equals to 0.5, a density equals to 750, the change in pressure equals to 800, and then the area of the cross-sectional area is equal to 20. So we substitute it inside. It can come up with the velocity is 3.4559, and then the volume flow rate will be 69.118. So here comes the maximum 1 and maximum 2 value. Okay. So next is the maximum value. That means we need to take the maximum range, maximum value in that range, all combine that and then put it inside to the value. And then we can come up with V equals to 6.5757, and then the Q equals to 328.785. So come up with this, we are using the code block to prove it, and then we can find that the answer is exactly the same. So that means this loop and then this function are running well because the calculated value and then their PC value are exactly the same. So the third objective that we need to achieve is to determine the relationship. That means we need to consider that if the certain parameter is increased or decreased, how this affect the final value of the velocity and the volume flow rate. So as we can say that in the changes of the height. So the first diagram will be change of the height, and then is from 0.5 until 1 until 1.5. So as we can see that the other parameter are remain constant. So volume flow rate will be increased and the velocity will also increase. Okay, the second one will be the change in pressure. So as we can say that the change in pressure is from 750 until 1250 and then 1750. It increase gradually. So the output result velocity of the water or velocity of the liquid and the volume flow rate will also increase gradually. That means these two parameters is directly proportional to the both volume flow rate and velocity. The next, the density. So as we can see that the density is increased from 500, 750 and 1000, then it's given then the result will be decreased. So the volume flow rate and the velocity will also decrease. So with this result, we can prove that the smaller the density, the bigger the desired output. So for the fourth objective, so we will decide the cross-sectional area, and then we fix all the parameters. We'll fix the height, we fix the density, we fix the difference in pressure, but we change the cross-sectional area of the pipe. So as we increase from 20, 30, and 40, we can see that the volume flow rate is increased. The velocity is remain constant because the area, cross-sectional area is not involved in the first function, but the second. The second is involved, so it will increase gradually. So as the cross-sectional area increase, the volume flow rate will increase. The cross-sectional area is directly proportional to the volume flow rate. Okay, as the conclusion, we can say that the value from the coding and the theoretical are the same. That means this function can run well if they are setting with a certain maximum limitation. So with the constraint and the condition we set in this previous report, we can get it the maximum fluid velocity is 6.5757 and the maximum volume flow rate will be 328.758. So this is useful if we are using this in the fluid mechanics solving problem. So the height and the pressure is directly proportional to the output value. That means if we increase the height of the pressure, so it will increase the output value also. But the density will be inversely proportional to the output value. So as the density increase, the output value will increase. But inversely, if density increase, the output value will decrease. So the last will be the cross-sectional area of the pipe is directly proportional to the volume flow rate. Okay, since the volume flow rate is Q equals to AV, that means if A increase, Q will also increase. So they have the dose relationship. So the last will be cross-sectional area of the pipe is directly proportional to the volume flow rate. So as the area increase of the pipe, the cross-sectional area of the pipe increase, the volume flow rate will increase because Q equals to AV. So based on all the conclusion that we listed, and then we already fulfill and then achieve the objective. So based on the report and then we have achieved our objective. Thank you.